All right, so now our discussion of dot diagrams, or these Lewis structures is what they're referred to as. I have summarized here the 5 steps that we're going to follow from the handout that I gave you. And the handout that I gave you is on the website, or it looks like this, drawing Lewis structures. And there's really, it's just the first 5 steps into drawing these. I'll start from the beginning, though, and in order to do that, step 1 is, all right, so I'm going to work my way across the top here. So the first one that I am going to do a Lewis structure for is SiCl4. And step 1 is you got to count the electrons. So I'm going to be jumping back and forth here a little bit. But number 1, calculate the total number of outer shell electrons, taking into account any charges. Add electrons for negative, subtract for positive. And what we're talking about here is, again, we're doing Cl4, is we want to look at the periodic table and count the outer electrons. Now, there's 3 ways you could do that. You could count the S's and the P's. That's the complicated way. You got to know some chemistry to do that. So Si is right here. I have 2 in the S and 2 in the P, so there are 4 electrons because of silicon. That's one way. The second way you could do that is you could look at the group number. So look at the group number on the top of the column, and Si is in group 14. Now, when we're talking outer electrons, remember, we don't include Ds, and there's 10 Ds. So that means in group 14, there are 4 outer electrons. So group 14 has 4, group 15 has 5, group 16 has 6, etc., etc. The third way, and probably the best way, is by looking at the A group elements. Now, this periodic table that I copied here doesn't have the A groups listed, but most periodic tables do. And what that means is, this is Roman numeral 1A, this is 2A. These are B's or none, so then 3A, Roman numeral 4A, so 4A, 5A, 6A, and that's about as ugly and sloppy as you can possibly be, but 7A, and then 8A, the I, A. Now that means the A group elements tell you how many outer electrons there are. So group 4A is 4, group 5A is 5, group 6A is 6. All right, so going back to our count, so we have 4 because of silicon. Each chlorine has 7 because it's in group 17. So group 17 has 7, or group 7A, times 4. So 7 times 4 is 28. So 4 plus 28 is 32 electrons. So what we're going to do is we're going to be able to tell a lot of things about this particular molecule by drawing what is known as a Lewis structure, or a Lewis electron dot diagram. All right, so I needed 32 electrons. Step 1, check. I counted the electrons. Like I said, I'm going to refer back to this handout. Keep skipping it. And number 2, in a species with more than 2 atoms, decide which atom is the central one. So there's a vocabulary. Central would be obviously the one in the middle. It is usually the least electronegative. So usually the least electronegative, but never hydrogen. Use 1 pair of electrons to form a covalent bond between the terminal atoms and the central atom. So we're going to take a pair of electrons and we're going to form a covalent bond between the central atom, with the one in the middle, and the terminal atom, which will be the one on the outside. So going back to this, so Si is going to go in the middle. Why? Well, officially it's the least electronegative, but really the simple way to do that is there's only 1 silicon. So whichever one there's only 1 of, it's probably going to go in the middle. So there's 1 Si, so it's going to go in the middle. If you look here, there's 1 P, so it's going to go in the middle. There's 1 C, there's 1 O, there's 1 Mg, there's 1 B. So that makes it a lot easier when there's only 1. We're going to deal with it over on the other column when there's not. All right, so Si in the middle. We're going to form a covalent bond between each of the terminal atoms by using a pair of electrons. So I'm going to go to attach each chlorine, and I've now formed a covalent bond. Next step. Step 3, arrange the remaining electrons to complete the octet, or the expanded octet, we'll come back to that in a minute, of the terminal atom. So arrange the remaining electrons to complete the octets of the outside atoms. All right, so I know that I'm going to have to add 6 more electrons to each chlorine, because right now it's sharing that 2 with silicon. So I need 8, so I'm going to put 6 more. 6 more, 6 more, and 6 more. So I've now Step 1, counted the electrons. Step 2, I attached the terminal atoms using a pair. Step 3, I finished the octet of the outside ones. All right, step 4. Any remaining electrons, so after you complete the octet, you count how many electrons you've used, and any remaining ones are added as a pair to the central atom. All right, so I've used up 8 plus 8 plus 8 plus 8 is 32. I used up 32 electrons. I only had 32 electrons, so I don't have any left over. And then the last step is check to see if you have an octet on the atom in the middle. If you do, you're good and you're done. And if I look at the silicon, I have 2, 4, 6, 8 around that silicon, and so I'm finished. So this is the Lewis structure for SiCl4 and its 32 electrons. Now what we're essentially trying to do is figure out how many bonding pairs and how many non-bonding pairs are around the central atom, the one in the middle. Now a bonding pair is going to be that pair we use to connect the two. A non-bonding pair is going to be a pair that is on silicon, but it's not attached to any other atom. So bonding is shared between two. Non-bonding is only on the one in the middle. In this one, we have 1, 2, 3. We have 4 pairs of bonding electrons. And we have 0 pairs of non-bonding electrons. And so what we refer to then is some kind of chart or table which has 4 and 0 bonding. And I didn't bring that up. I can grab it quick. That we use in my class. Let me just click here and my notes on VSEPR handouts. So here we go. So you can see the number of bonding pairs, the number of non-bonding pairs. The one we just did at 4 and 0. So here's some information that we can see about this. Here's an example of it. Here is the bond angle. So we have a 109.5 bond angle, degree bond angle. It's called a tetrahedral arrangement of the electrons. The geometry of the atoms has a name of a tetrahedral. Here's an attempt at a three-dimensional shape. The straight lines here being in the plane, the dark one coming out towards us, the dashed one going into the board at 109.5, and then a general AB4, a general formula for a substance that could be 4 and 0. So that's what we're trying to do. So we can find out lots of things, and then what we're going to learn is it's nonpolar. And we can tell that based on all of this. All right, so let me do another one. Let me get rid of this one. Oops, I don't want that. Okay. The next one is PF3. So once again, I'm now just going to refer to the steps right here. And then we'll worry about the ones that don't have an octet when we get there. And we'll deal with those. All right, so phosphorus. Phosphorus is right here in group 15, so 5 electrons. Remember, 15 has 5, 16 has 6, 17 has 7. Or group 5A. So phosphorus has 5. That's in group 17. So 7 times 3 is 21. So this time I have 26 electrons to arrange in my Lewis structure. Figure out which one goes in the middle. I told you it's the one you have one of, or the least electronegative. But phosphorus in the middle. Now this time, instead of doing dots, I'm just going to attach them with a line, a dash like that. And that dash represents, so it equals a pair of electrons. So really I've used 2, 2, and 2 to connect those, but it just makes our diagrams look neater. All right, so I've attached the terminal atoms. Check. Finish the octet of the terminal atoms. So I'm going to place 6 more dots around each fluorine to give it 8, because it had 2. Remember that line represents 2, and then 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, and 8. All right, so now I have attached all of the terminal atoms and finished their octets. So finish the octets of the terminal atoms. Add the remaining electrons to the central atom. So now I have to count how many have I used up. I've used 8, 8, and 8. So I've used up 24 electrons. Well, I had 26 electrons. So that means I have 2 extra ones. And so you add the remaining ones to the central atom as a pair. And then check the central atom for its octet. Well, it has 2, 4, 6, 8. So I've used up all 26 electrons. Everybody has their octet. So I'm good. So now what I wanted to do again is count the number of bonding and non-bonding pairs. So I have 3 bonding pairs. Again, bonding pairs are the ones that connect other atoms to the central atom. And this time I do have 1 non-bonded pair on the central atom. So that's what it would look like, those 2 extra dots. And then if I wanted to refer back to my chart here, you can see we have 3 and 1. So here's 3 and 1. An example would be NH3. You can see the bond angle. it's a tetrahedral arrangement again. This time the geometry is called a trigonal pyramid. And then, again, an attempt at a three-dimensional shape. And then, again, a general form, AB3 with this extra electron pair. So an extra electron pair. All right, next one. CH4. Let me clear those. CH4. All right, so carbon is in group 14 right here. Group 14 has 4, or group 4A. So I have 4. Hydrogen is right here in group 1. So that means it only has 1. And I have 4 of them, so plus 4, 1 times 4. So I have 8 electrons. 8 electrons. Counted the electrons, good. Which one goes in the middle? Well, carbon, because I only have 1, or the least electronegative, so carbon's going to go in the middle. I'm going to attach the hydrogen using a pair of electrons. Remember, we're not going to do dot, dot, and connect it. It looks nicer when you do a line. So that's 2, 4, 6, 8 electrons. Now, the next one is finish the octet of the terminal atoms. Now, hydrogen's a special case. What makes it special is it's in this first row of the periodic table. And in the first row of the periodic table, what we've learned is you don't have P's. You only have S's. It's 1s1, 1s2, and it's full. So that means hydrogen, when we go to do the dots, we're not going to put 6 dots around the outside here. We're not going to do that. And the reason we're not going to do that is it can only hold 2. So by placing this line right here and connecting these hydrogens, hydrogen's satisfied. It has its 2 electrons. So then I finish the octet by simply making the bond. Add any remaining ones to around the one in the middle. Well, I have 2, 4, 6, 8. I don't have any extra ones. And then the one in the middle, again, has its octet. And so carbon's happy. This would be 4 bonding and 0 non-bonding, so it would be just like SiCl4. Same general shape. And what we're going to learn again tomorrow is that it's nonpolar. It has some symmetry associated with it. Okay, next one. H2O. All right, so 2 because of hydrogen. Why? Well, it's in group 1A, or group 1 times 2. Oxygen's in group 16, so 6, or group 6A. And so once again, just like the last molecule, I have 8 electrons. Oxygen in the middle, the lesser electronegative. Now, that's not true in this case, but generally it's true, and it's definitely the one I have 1 of. All right, so I'm going to attach the hydrogen. So I'm going to stick an H and an H. Now, does it matter where I put them? Can they be up here? Yeah, it doesn't matter. We're trying to do a 2-dimensional arrangement of a 3-dimensional object. And, you know, it doesn't really matter how you draw this. What matters is if you can count the number of bonding and non-bonding pairs so that we can refer and figure out what that shape looks like. So don't stress over where you put your hydrogens. If I stick it there and you put it here and here, because remember, water is actually the Mickey Mouse molecule, and, you know, it's normally drawn like that. Again, it doesn't matter. All right, so I counted the electrons. Check. I attached the terminal atoms using 1 pair. Good. I have to finish the octet of the terminal ones. Done, because it's hydrogen, and hydrogen can't get 6 more dots around it because it's in the first period of the periodic table. It can only hold 2. I've used up 2, 4. I had 8. So attach any remaining electrons to the central atom. So I'm going to put 1, 2, 1, 2. So remember, they go as a pair. And so I've added 2 pairs. So now oxygen doesn't have its octet. 2, 4, 6, 8. It does. Number of bonding pairs would be 2 bonding pairs. And then there would be these 2 non-bonding pairs. So if we're referring back to this chart, you know, we have 2 bonding, 2 non-bonding. 104.5. Again, a tetrahedral arrangement. It's called a bent or V-shaped molecule. A 3-dimensional attempt there. Again, these would be in the same plane, and then a dark one coming out towards us and a dashed one going into the board. And then AB2, E2. My column got a little messed up there. All right, so that's the last of the simple ones, where we didn't have to, you know, modify our model. The problem with models is, you know, as we come across exceptions, the models start to become more and more complicated. And here comes the first one. All right, so MgI2 is our next molecule, MgI2. Mg is in the second column, group 2A, 2 electrons. 17th column, so group 7A, 7 times 2 is 14, so I have 16 electrons here. Mg in the middle, for sure, I have 1. Attach the iodines. Good. Finish the octet of the iodines. So that gets me right through step 1, 2, and 3. Count how many electrons I've used. Any extra ones go around magnesium. 2, 4, 6, 8. 2, 4, 6, 8. So I've used up 16 electrons. I only had 16 electrons. But here comes the issue. Check the octet on the central atom, and magnesium does not have its octet. It only has 2, 4 electrons around it. Uh-oh, what do I do now? Well, let's refer back to my sheet, and we're going to go right through the steps. Step 1, calculate the total electrons. Done. Number 2, attach using a pair. Done. 3, finish the octet. Done. Step 4, any remaining ones? We didn't have any. So step 5, if the central atom lacks an octet, you can form multiple bonds, and we're going to learn how to do that in the next video. Exception. Here's our exception. If the central atom is in group 1, 2, or 13, so group 1A, 2A, or 3A, hydrogens, lithium's column, beryllium's column, and boron's column, they are stable without achieving an octet due to symmetry. It actually goes 2, 4, 6 dots are okay. Well, we're doing magnesium, so 4 dots are okay. So it has to do with symmetry. Things that are symmetrical are stable. So due to symmetry, this one does not need its octet. So check, that is a good Lewis structure. So there's our first exception that we have to pay attention to in our model. So the number of bonding and non-bonding pairs, it would be 2 bonding and 0 non. And once again, we could refer back to our chart here. We have 2 bonding and 0 non. And bond angle would be 180. It's called linear, and there's a 3-dimensional attempt at a picture in 2 dimensions. That one's plane in the same plane though, so pretty easy. All right, next one, BF3. So I'm going to start going a little quicker here so I can get done with this, because I don't know about you, but I'm getting bored. All right, so BF3. BF3, 3 dots, 21 dots. Why? Group 17, 7 times 3 is 21, so I have 24 electrons. Boron in the middle. Attach the fluorines. Finish the octet of the fluorines. I've used up 24 electrons. I had 24 electrons. There's no extra ones to go around boron. Boron does not have its octet, but it is in group 13. So group 13, or 3A, these only need 6 electrons around them to be happy, once again, because of symmetry. This thing would be symmetrical. It would be, exactly 120 degrees between each other. Symmetrical, 3 and 0. We could refer to our chart, and we could see that that would be the case. All right, next one. ClO3 minus 1. So the reason I undid this one, obviously, is because it has a charge. So what do you do when it has a charge? Well, 7 electrons because of chlorine, because it's in group 17, or 7A. Oxygen's in group 16 times 3, so 6 times 3 is 18. Now, this has a -1 charge. What that means is an electron was added to give it a negative charge. This is the polyatomic ion chlorate. Chlorate, ClO3 minus 1. So 7 and 8 is 25 plus 1 is I have 26 electrons to put into this. So I have chlorine bonded to the oxygens. Finish the octet of the oxygens. I've used up 24 electrons, so I have 2 left over, so they're going to go around the one in the middle. And then does the one in the middle have its octet? Yeah, it does. We're back to the easy. So 2, 4, 6, 8, it's happy. Everybody's happy. So now when you have a charged ion, the convention is to put it in brackets and put the charge on the outside, like so. So that would finish it off. And then to count bonding and non-bonding, I would have 3 bonding pairs and 1 non-bonding pair. And so again, we could refer to that chart and figure that out. All right, next one. NH4 with a +1. All right, a +1. All right, nitrogen's in group 15, so 5 dots. Group 1, I have 4 of them, so 4. Now, it's a +1. And a way an ion can become +1 is to lose an electron, so we're going to take away an electron this time. So 5 and 4 is 9, -1 is 8, so we have 8 electrons. Nitrogen in the middle, hydrogen, 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 and hydrogen. My 4 hydrogens attached to it. Finish the octet of the hydrogens. Remember, hydrogen's done once it forms that 1 bond because it only needs 2. I've used up 2, 4, 6, 8. I've used up all the electrons, so nitrogen doesn't get any extras. And nitrogen has its octet, 2, 4, 6, 8. Finish it off, because it is an ion, by placing it in brackets and putting the charge on the outside. Done. All right, so the last of the exceptions for today, then, is dealt with in PI5. PI5, 5 electrons, group 15. 7 times 5 is 35, so I have 40 little guys to put into this electron dot structure, Lewis structure. So phosphorus in the middle for sure. Now here's where we start to get a little bit screwy. You see, we want to make things nice and neat looking on our paper. Top, bottom, left, right, north, south, east, west. And we want to make this thing look nice and symmetrical. But remember, what we're trying to do is a three-dimensional object in 2 dimensions. And so there's limitations. So don't get stuck on top, bottom, left, right, top, bottom, left, right. Because this one you won't work because you have 5 things you have to attach. All right, so step 1, I counted the electrons. I've attached them. I'm going to finish the octet of those by placing 6 more dots. Now, something I tell my students is you don't have to put these dots in there as long as you know they're there. Just leave them off. But when you go to count, you're going to go 8 plus 8 plus 8 plus 8 plus 8. So I've used up 40 electrons. I had 40 electrons. And so I'm good. The last one, check for an octet. Uh-oh. 2, 4, 6, 8, 10. Phosphorus has 10 electrons around it. Octet means 8 electrons around it. Well, what you're going to find is, as long as it has 8, it can have 10. It can even have 12 electrons around it. When, and our last exception here, elements in the 3rd row of the periodic table and lower can have more than 8 electrons. It's called an expanded octet. So you can have an expanded octet if you are in the 3rd row of the periodic table. So the 3rd row, right across this row, there's phosphorus, so it applies, or lower. So these guys over here can actually have more than 8 electrons around them. And be stable. Has to have at least 8, but it can have 8, it can have 10, it can even have 12. All right, so that is the last bit of the exception. So let me do the last one up there in the corner, CLF5, and then we'll call it a day. CLF5, 7 plus 35 is 42 electrons. I have 42 electrons. That's a lot. Chlorine, nice ugly chlorine there. Let me fix that. Chlorine bonded to 5 fluorines. Remember, don't get stuck on north, south, east, west. Finish the octet of the fluorine, so I'm not going to write them in this time. I'm just going to know I got 8, 8, 8, 8, and 8. So 8 times 5 is 40. 42, where do I stick them? Well, again, remember, it doesn't matter. 42. The 2 are going to have to go around the chlorine. When I count the number of bonding and non-bonding electrons, I'm going to have 5 bonding and 1 non. And the last one I did, I would have had 5 bonding and 0 non. Both of those are on our list here down at the bottom. There's 5 and 1. And there's 5 and 0. So you can see what the 3-dimensional pictures are going to look like. You have 5 and 1 here. And that's what tomorrow is going to bring. So if we were going to do the dots for this, we would have, chlorine in the middle. We're going to attach a pair of electrons down that way. We would attach a fluorine this way. And then in the plane here, we would have 1 fluorine. And then the next one is going to be coming out of the board towards us. The other one is going to be going into the board away from us, all in here at a 120-degree angle from each other. And so, again, don't get so caught up in where you're putting your fluorines and your dots when you do your Lewis structure, because it's a 2-dimensional picture, of a 3-dimensional object. And sometimes it just doesn't look okay. And it may not look exactly the same as the one your friend did. But as long as you can count the number of bonding and non-bonding pairs, you are okay.